Hi, Seth here. Welcome to the channel. Flux has a learning curve and is quite different from Stable Diffusion. To make things easier, we combined the custom nodes into one Flux sampler node. Flux deals with pixels rather than resolutions. For that, we made the Flux resolution calculator and a getImageSize node that also gets the ratio for easy image to image. Image to image has never been more straightforward. With Flux and my custom workflow, you can take an input image, pass it through a large language model, and get creative results without any adapters or control net. And I have tried this with a range of images. Not only that, but you can also control the creative output. Take this bedroom example. I have done an image to image, but I managed to get 3 different results based on slight prompt modifications. This also opens up other creative options, like changing the subject while maintaining the style of a reference image. The examples shown so far are without any inpainting, control net, or adapters. This is an actual 1-to-1 ratio output size. The workflow is also designed to consistently upscale up to 5.04x the input resolution on consumer-grade hardware. Passing a simple text prompt through the LLM will give you some fantastic results. With Segment Anything version 2, Florence, manual masking, you can inpaint and get creative results. So, I have created just one workflow that does all this and is very much automated. Let me show you my workflow and some hacks and tricks I use to achieve these results with Flux and ComfyUI. I want to thank all the paid channel members for their continued support. The Flux 1 models are designed using a hybrid architecture that combines multimodal capabilities. It can handle various types of data with advanced processing techniques. Specifically, these models utilize parallel diffusion transformer blocks, which means that they employ a diffusion-based approach in combination with transformer architectures to process and generate data efficiently and effectively across different modalities. This design aims to improve performance by leveraging the strengths of both diffusion models and transformer architectures, making the Flux 1 models highly adaptable. You cannot treat Flux like SDXL, as it is not stable diffusion. I have been testing Flux in and out since it was released. The image-to-image quality for Flux is so good that it almost renders control nets and adapters redundant to a certain point. Combining Flux's core model with T5XXL leverages the strengths of both models to achieve superior results in AI image generation. Running an LLM model within ComfyUI is crucial for Flux. Even simple prompts enhanced with LLM can drastically change the image. This workflow is a basic Flux workflow which includes inpainting and image-to-image. However, due to its complexity, you must be fully fluent in Comfy and have prior experience with SDXL and related models. I will build the workflow from scratch, making it easy for you to recreate. In the end, I will make all the necessary adjustments for Schnell. Also, we'll explain why we created some basic nodes for this workflow as we go along. To start off, let's look at the custom nodes used. Impact Pack for some very good logic switch and flow execution. Python Gauss for show and save text and some math expressions. Ultimate SD Upscale for the second last stage upscale. ComfyUI Studio for some string nodes. Comfy Math for some integer conversions. ComfyUI Logic for some logic nodes and RG3 for workflow organizations. ComfyUI Essentials and Kajai nodes. Florence 2, Segment Anything 2, and Layer Style. Ollama for the LLM prompting. Lastly, Control-Alt-AI nodes for the Flux sampler, resolution calculator, and Boolean logic. Go to ollama.com and download it for your computer. Use the pull command to pull the 2 models. Do not use the run command to run the model because in the workflow we would be offloading the models to save VRAM. I will leave all links in the description. For text, use the Llama 3.1 or higher model. And for vision, the Lava model. Remember, always start the Ollama app from the Start menu before starting Comfy, and do not run any models from the command prompt. You will find the Flux Safe Tensor files from Hugging Face. Download the Schnell or Dev model as needed. Also download the ae.safetensor file. This is the VAE. The model files will go in the Diffusion Models folder. The AE Safe Tensor goes in the VAE folder. I will be using two different upscalers. OpenModelDB is a very good website for finding good upscalers. These upscalers are hosted on Google Drive. You need to download them from the link on the website. Both the upscalers link will be in the description as well. Put the downloaded upscalers in the Upscale Models folder. Unlike traditional models that focus on fixed resolutions, Flux operates effectively across a wide range of pixel counts, from 0.1 to 2.0 megapixels. This flexibility allows it to maintain image coherence and detail regardless of the pixel count. The model is trained on images with diverse aspect ratios and resolutions, which is why we need a Flux Resolution Calculator node. The node is dynamic in the sense that it has a mathematical formulation. 0.1 megapixels would be as low as 320 pixels, with 2.5 being about 1568. At this stage, I would not recommend anything higher than 1 megapixel, but feel free to experiment. I got blurry images at resolutions higher than 1 megapixel with the dev model. The node will round off the resolution and make it Comfy compatible. I got excellent results in all ratios except 32:9. For that ratio, I sometimes saw double human subjects. However, there was no stretching or hallucinations. In the workflow, I will use a lot of set and get nodes from Kajai. They really help streamline everything. Add 2 set nodes and set the width and height. Let's try a custom ratio, say 5:11. When the custom ratio is enabled, it ignores the aspect ratio, and when disabled, it ignores the custom aspect ratio. We will organize the workflow as we go. Group these and name them resolution calculation. Add a load image along with the get image size and ratio node. The idea here is you can take any image, and the workflow will make it Comfy and Flux compatible depending on the ratio you select. Since the workflow will allow you to use the image as a reference, as well as image to image, you have the flexibility to use a different aspect ratio when using the image as a reference and the same image aspect ratio when using it as an image to image. Set the image ratio and rename load image to image conditioning. Use a get node and set it to image ratio. Right-click to convert the custom aspect ratio to input and connect it with the image ratio. This is set up so that when you want to use the image's aspect ratio, you just enable the custom ratio. For image to image, we need to resize this image. Add an image resize node, the one with the wrench icon. Convert the height and width to inputs. Make the connection with the load image. Add 2 get nodes and connect with width and height. Choose Lanxos and keep proportion. Add 3 set nodes. 2 for the resolution and 1 for the resized image. Create a group for these nodes and name it image input. Add a CR text node for the text conditioning. So here, with this text conditioning, you can put in anything you like. You don't have to structure your prompt. We will pass this input to an LLM model which will structure and expand on it with details. Create a group called text input. Add an Ollama vision node. This will be used for image reference and image to image. Also add an generate advanced node for text conditioning. Connect the nodes as shown. A note here, connect the original load image node to the LLM rather than the resize. It gives better prompt outputs for some reason. Rename to image and text LLM. Let's put these nodes aside. I am now going to add image and text logic. Basically, the idea is to enable and disable the LLM chain based on the input. I have to do this to optimize the workflow since Flux is a bit heavy on VRAM. Add a switch from the impact pack and rename it as shown. I want to add 3 options here: image, text, and disable LLM. So based on these input, the whole workflow will move in a specific direction. Add 2 Boolean basic nodes and connect them with the switch. We'll explain the logic with the display any node. Rename the inputs for clarity. The bridge control node is actually excellent for this logical workflow control. Don't duplicate this node once you make an input connection. Always add a new node. This node takes in any input and makes a pass-through. It then converts the output to the matching input. So here, if I connect the image, you can see the output changes from value to image. At any given time, this node will act as a pass-through, taking the input, if any, and passing it along to the connecting node. If there is no input, then the connecting node will give an error. Active mode means the connected LLM node will remain active. If you turn off active, you then have a choice to bypass or mute the connecting node. The logic I am thinking here is to control the active mode via Boolean true and false. Convert the mode to input. Now, connect the Boolean output from the switch to the control bridge. Note that both Booleans are false. Switching 1 or 2 will keep the LLM muted. Let's go over this slowly. First, let's make the image LLM work. For that, we need to change the Boolean to true. Selecting 1 now enables the node, and 2 disables it. Rename the bridge to image LLM control. Add another control bridge, rename it to text LLM control. And connect the text conditioning. The control parameters will be the same as those for the image control. The core logic will remain the same. We need to reverse the logic for the text only. Add a Boolean reverse node. Convert the Boolean to input. Make the connection with the switch and the text LLM control. The nodes will now work as intended based on the input selected. Let's add the custom conditioning, where you want to disable both LLMs. This may be required for complete control. For example, you can use the LLM to generate the original prompt and then use custom conditioning to modify it. Once the model is offloaded from the GPU, the Vision LLM can generate different prompts. We will save all prompts via a node. If you like a specific one, use the custom conditioning to continue working on the same image and maintain consistency. Also note that we need two sets of prompts, a larger one for the T5XXL and a summarized one, which is under 80 tokens for the clip L. This applies to images, text, and custom conditioning. When using custom conditioning without LLM, use a more coherent language format. For summary, input short keywords. Set the output to custom conditioning. Then, duplicate and create another output for custom summary conditioning as shown. Move back to the logic nodes. Connect the first Boolean basic to input 3 and rename to disable LLM. The problem is that when we select the third option, both nodes should be disabled, meaning both should get a false input. We won't change the core logic to achieve this, as that works for the text LLM. We need to modify the image LLM logic. Here, add a compare logic node. If you notice, the switch node has a select label and a select index output. The select label will output the custom rename label as per selection. The index gives an integer output. For this to work, I have to change the logic of the image LLM. Instead of a standard Boolean, we will use the equality operator to compare integer values. If the values match, it gives a true Boolean output. If not, it will give a false Boolean output. Connect the select index to A. Then add an impact integer and connect to B. Change the integer value to 1. Now, it will only give a true output when you have selected the image LLM. For switch option 2 and 3, the output will always be false. Connect the compare node with the image LLM control, and let's test. Organize all these nodes within a group called Image Text Logic. Add 3 set nodes. Connect the select label to one of the set nodes and name it input label. Connect the compare Boolean output, which would be called image Boolean. Lastly, connect the Boolean reverse and name the set node text Boolean. We require these at a later stage in the workflow. I will now build the entire text LLM. Previously, I connected the bridge to context just to check the logic flow. Let's enable the LLM and disconnect the bridge from context. Convert the prompt to input and connect the text LLM control again. Ensure that Llama 3.1 is selected as the model. The keep alive setting for all Ollama nodes should be 0. This will load the model on the GPU, and as soon as the node is done, the model will be offloaded. If you don't do this, you will run out of VRAM using Flux. Put in a random seed and choose Fix or Randomize as per preference. Keep the remaining settings as they are. This area contains the system instructions. Use the exact same prompt as I have used. This ensures a clean and structured response. I will post these in the description for easy copy and paste. We are telling the text LLM to generate a detailed response based on user input. Since this would be for the T5XXL, the token limit is around 512. Connect it with a showText node, rename and test. You can see the LLM gave a very elaborate prompt, which is exactly what will give you quality outputs. The prompt includes describing the atmosphere, moods, style, lighting, colors, shadows, and overall theme. And this is all that I put in. You don't even have to structure sentences, just typing in keywords will do the same trick. However, the more you explain, the better the prompt will be structured. Another thing I like to do is copy and paste this into the custom conditioning, disable LLM, and then fine-tune it according to my preferences. This is the best way to get good results with Flux. Detailed long prompts up to 512 or fewer tokens. We need to shorten this for the clip L Flux conditioning. The clip L only supports around 77 tokens. Duplicate the text LLM and show text node, make the connections and rename as shown. Change the system instructions to the following. Now, we are telling the LLM to take the previous response, since that's the input, and summarize it to a concise version, less than 80 tokens. I just rounded the 77 to 80. The response tokens will go a little up or down anyways, depending on your input. Let's test it. You can see it kept the most important stuff, like the defined text, the subject, and so on. Add two set nodes and set them as text LLM and text summary. This will be needed later in the workflow. Now we should ensure that the switch logic is passed on to the summary LLM as well. Add a new bridge control and rename it to text summary control. Like before, convert the mode to input. Connect the value inputs and outputs. Add a get node. Select text boolean and connect it with the summary control. This is the same logic we defined earlier. Let's test it. Okay, so you can see the problem here. This won't work. The bridge control node needs an active input node to control the connecting node. Since the text LLM is muted, the control node will not mute the summarized text LLM. There is a simple solution. Add a CR text node in the text input group and set it as blank. Now add a switch any node from RG3. This node works by passing on with whatever is the first available input, ignoring the rest. The first input should always be text LLM, and the second one should be the blank. This way, whenever the text LLM is enabled, it gets priority, and whenever disabled, the blank ensures connectivity to the bridge control and mutes the text summary. Let me show you with a display any node on how and why this works. Now let's deactivate the LLM via switch and see what happens. You can see the 1, 2, 3, 4 input. Remove it and keep it blank. And you can see in the backend it sends quotes, but it's blank. Connect with the control summary and test. It works. We are going to apply a similar logic to the image LLM, but it is a bit more complicated. Group these nodes and name the group as text LLM conditioning. Recording the video took me several days. During the recording process, the bridge control node was updated to include a stop function, and the node interface is now clearer. We are not going to use the stop function in the workflow. The new interface has a drop-down instead of a button for behavior. Just use mute wherever mute is there and bypass wherever the workflow has bypass. All other behavior of the node is exactly the same. If you haven't updated, you will see a true on the existing node after the update. Change to mute or bypass as necessary. For the image LLM, ensure that the model selected is Lava, which is a vision model. Change the Keep Alive setting to 0. Use the exact same prompt, otherwise there will be issues with the responses. The prompt is structured in a way that LLM is instructed to first analyze and categorize the image as a vector, painting, photograph, and so on. Then, describe it in detail, including its composition, style, mood, colors, etc. The only issue I find with the vision node is that there is no seed here, so every time you run it, it may give you different responses. Hence, we will add a save prompt text node at the end to save the initial prompt if needed. Duplicate the show text and summary nodes and rename them as shown. There will be no change in the summary system instructions. Keep it as it is. Add the switch logic control to the summary node, as we did previously for the text summary. The bridge control will also be precisely the same. Set it on mute. Select the image Boolean logic for the behavior. Let's enable image LLM and check out the response prompt for this image. It gives an excellent, detailed description of the image. Let's check out the summary. The summary won't always be a single line, it will vary from image to image. Let's say you are doing image to image, but you like to modify the image and want a modified prompt in between via LLM. Duplicate the summary LLM node. I will include this system instruction in the description as well. Here, you have to change the text between the quotation marks. All this drama has to be done because of the prompt response structure. After a lot of testing, I found that 99% of the time, this instruction changes the prompt as desired, maintaining the original prompt overall context. Basically, the instruction tells it step by step what to do, how to do it, and how to structure its response. Rename the node, and we need to now add control logic to this node as well. Add another control bridge node, rename, connect the inputs/outputs, and set the behavior to bypass. The control logic for this node will be semi-automatic, so we need to add a switch. Copy the image text logic switch and Boolean and paste it here. Convert the mode and make the connection. Rename and remove the third input. Reverse the Boolean logic so that the node is bypassed on input 1. Independently, this works. Now copy the show text node and connect it. Then let's try to modify a vision prompt. The Vision LLM has detected a dog. Let's add instructions to change the subject to a cat. Let's compare it with the original. This has accurately changed the subject while maintaining the overall context. If you go too crazy with the modification, sometimes it slightly changes the context. What I like to do is in image to image, modify the prompt, then copy the modified prompt and summary, use custom conditioning, and manually fine-tune. Overall, the use of LLM in the workflow is very flexible. This switch logic is not entirely correct. It's independent of the original switch, which makes it a problem. As long as the image LLM is enabled and this is switched to bypass, it will work. Under any other condition, it won't. The first problem is solved by adding a blank get node to an RG3 switch any node as we do for all summary bridge controls. This will create a new problem when the image LLM is disabled and the switch is set to modify. You won't get the context error if it is set to bypass. This error is caused by the blank prompt and the LLM having nothing to process. Solving this second problem is a bit more complicated, and you have to link the current switch logic with the original input switch logic. The complexity comes from the user's ability to modify or continue with the original prompt. We have to give the user the same ability but ensure that there is an extra logic condition to apply and enable the node, only and only when image LLM is enabled. If the LLM is disabled, then the logic should be that it should ignore the user input to continue or modify the prompt and bypass it anyway. To solve this, we will create a separate modify image logic in addition to the existing logic. Add a string and type modify with a single space. Use the get node and set it to input label. This is what we set out earlier in the tutorial. Concatenate both these text inputs using a ComfyUI Studio node. Verify that the output is correct. The output will depend on the input switch selection. It should always be modify, space, followed by image, text, or disable LLM. Set this output as modify logic. Test if the text output works correctly. Add the nodes to a group called Modify Image LLM Logic. Add a logic compare node. You won't be able to connect the string output to the existing switch. So add a new switch and connect the same image any string to both input 1 and 2. Delete the previous switch and connect this string output to value. Connect the selected label to A. Use the modify logic from the get node and connect to B. And let's test this first. It should trigger true only when image LLM is active and switch selection is on modify, and for the rest of the time, it should ignore the continue or modify switch and trigger a false output. Now it is working as intended. Connect the Boolean to mode. Let's test it one last time. Deactivating and checking behavior. Okay, so everything is working. Let me show you some examples of modification via LLM. If you are using an image as a reference, here are some examples of how you can modify the prompt before passing through the clip in code. Image-to-image prompts are a bit different. I will showcase these later with one or two practical examples. In Flux, image-to-image has a different setting than using an image as a reference. We will add a control panel to enable image-to-image. We should ensure that the summary follows the same logic. If you modify a prompt, the summary should be as per the modification, otherwise, it should be as per the original prompt. Connect the modified LLM to any one and the original LLM to any two. And connect this with the summary any node. Add two set nodes. One is image LLM and one is image summary. Rename the summary control bridge for clarity. Add all nodes to a group and name the group as image LLM Conditioning. We will now define the final T5XXL and clip L conditioning. Add any switch along with 3 get nodes. The order should be image, text, and then custom conditioning. Everything will be collected here and passed on to the Flux Core nodes as final conditioning. Duplicate these nodes and change the input to their respective summary. Add show text nodes to both of them. Set the final output as Flux T5XXL and add a save text node from Python Gauss. Do the same for the summary output. Group, organize, and test. I am using the full 24 GB model, which requires a load diffuser node. With this workflow, I would not recommend the default weight. Instead, choose the E4M 3FN weight. A dual clip loader is recommended. If you have 32 GB system RAM instead of 64, choose the FP8 version of the T5XXL. For the tutorial, I am using the FP16 clip weight. Almost all of the Flux Core nodes will have a set node, as we require them in all upscale processes further in the workflow. For the LoRA, I recommend using only the LoRA model loader without the clip. Many people are having issues that the LoRA doesn't work. LoRA has to be loaded along with the Flux model on the GPU. If Flux takes about 90+% of your VRAM, the LoRA will probably not work. Also, Comfy was updated to improve LoRa's FP8 performance. Flux takes only about 60 to 70% VRAM on my system, so I have no issues using two LoRa's. I will link the two LoRa's I use from CivtiAI. Keep them at 0.5 strength each, and you have to daisy chain them as well. If you are going to not use the LoRa and bypass them, then ensure you connect another set node directly with the model. Add a Flux clip text and code, convert both to inputs, and get the clip outputs from the Get node. From my testing, going a bit lower creates more inaccuracies but increases realism, along with sometimes hallucinations. Increasing the guidance does the exact reverse. You won't be getting that well-defined details with lower guidance. For the tutorials, I am keeping it at default value. Flux has a model sampling node, which is directly related to the resolution of the latent. The base shift defines the minimum variance, and the max shift defines the maximum variance. Don't touch the base shift value. However, the max shift can be adjusted from 0.9 to up to 2. I will explain its creative implications with real examples later in the workflow. Add an SD3 empty latent and use the same width and height from the resolution calculator. The Flux sampler is a reamped K-sampler modified to be more attuned to the Flux model. I ensured that the code only accepts positive conditioning and removed the CFG setting. The CFG setting within this node is set at 1, and you cannot change it. I have increased the default steps to 30, but I recommend steps at 42. There is a vast difference in image details between 20, 30, and 40 steps. Above 45, it starts overstepping, and there is actually a loss rather than any gains. The image detail worsens at 50 steps. 42 seems to be the right sweet spot. I have also taken the liberty of removing all samplers and schedulers that do not work with Flux. The slowest over here is Hume++2, but it is also the most accurate and sharp in details. Euler is the fastest. All images showcased in the intro use the Hume 2 sampler with the beta scheduler at 42 steps. However, the beta scheduler should not be used when in painting. SGM uniform or simple works better. Make the remaining connections as shown and add the VAE decoder. Set the decode output as 1x image. Add the Purge VRAM node from Layer Utility. This is the only one that works as intended. Purge cache to save VRAM at each stage of the generation. Purge models for unloading all the loaded models. I will be using these throughout the workflow from this stage, which helps keep the VRAM usage at a minimum. Organize the nodes and name this group Flux Core. Image to image requires different settings. When you don't use these settings, you're basically doing an image reference. Image reference means you just get the prompt of the image from an LLM and generate something from scratch. In an image-to-image, we pass on the image into latent and denoise it at 75%. This gives structure to the image and acts as a very strong control net as well. Add 3 switches just before the Flux sampler. One switch is for the model, one for the latent, and the last one uses a different denoise value. Convert the noise C to input, and connect all the switches with the sampler. Rename the float and keep the denoise value at 1. Add a VAE encode node and connect it with the image-to-image output from the Get node. This is the reference image resized and defined very early on in the tutorial. Duplicate the model sampling flux. We will use the resized image width and height. Connect the model with the switch. Convert the max shift to input. We will add another switch to get creative control over the generation. Add 4 float nodes and connect them with the switch. Here are the values I would suggest starting with. 0.9 would be very close to the original image and will follow your modification less. For the default value, I like to keep it higher than the standard 1.15, so 1.25 would be the default. A value of 1.7 would make the modifications closer to your prompt. At a value of 2, you would see things start to change a lot, as per your prompt. We will only manipulate the image-to-image based on the max shift values rather than the denoise strength. This approach is very different but will give you stable and consistent results. Keep the denoise value at 0.75. Note that the denoise is extremely sensitive. A 0.02 shift, plus or minus, would make the image extremely close to or different from the original. Hence, I prefer not to touch it and use max shift. Feel free to go to lower and higher max shift values as desired. Name the group as image-to-image. Right at the beginning of the workflow, add an impact integer node and set its value to 1. Connect it with the set node and name it setting image-to-image. Organize the nodes in a group, as we will also add the InPainting switch setting here. Convert all 3 selects to inputs, and connect it with the Get node. Rename the denoise setting inputs as well. Let's do an image to image and use the modify prompt function to change the dog to an elephant. Change the setting to enable image to image. Always enable custom ratio when doing image to image. The custom ratio would be close to the original image within the defined megapixel. Change the input selection to image LLM. Ensure that the model is Llama 3. For all other LLM, it should be Llama 3.1. Switch to LLM modification and change the prompt as desired. Let the max shift be at default. I'm just adding a compare node to make it easy to compare to the original. You can try different max shift values when doing an image to image. If satisfied with the desired output, copy the prompt in summary, paste them into custom conditioning, and disable LLM. Manually change the subjects in custom conditioning and summary for consistency. To do a style transfer, switch to disable LLM. In custom conditioning, use a prompt entirely unrelated to the image. Change the max shift setting to close to original. Without image to image, I get this output. This is kind of a style transfer. You can see how strong the control net is that the cat is facing the left as the dog. Let's change the image to something else. The cat should now face towards the right, the same as the clock. And there you go. The text mess up is quite obvious, as I have used LoRA as well. It's a complicated text for this image. I have not changed anything except the reference image. So, for Flux, as of now, ControlNet is not as necessary for creative use as it was for the SDXL release. Any ControlNet or IP adapter should cover what is lacking rather than be implemented like it was for Stable Diffusion. I will quickly go over this example and explain the max shift functionality and how to use it. So, I am specifically using a living room as the original image, as it showcases how good Flux is. The idea here is to give the room a cyberpunk look and feel. Denoise is at 0.75. I am not touching that. This is at default value defined in the image-to-image setting. Changing to close to prompt and keeping the same denoise will add more cyberpunk elements while maintaining a similar output. Changing to a lower max shift will reduce the cyberpunk elements. This is a mid-journey generated image. You can see how the lighting is broken here, for example. At close to original setting, Flux fixes that. Using very creative settings deviates from the consistency a little bit. But try out values higher than 2. As for some creative use cases, I ended up using those values. In the settings group, add another impact integer for the InPaint settings. Get the image 1x output. Then add a Florence 2 run node. Change the task to caption to phrase grounding. If you don't have the models downloaded, add the download and load node. The preview bridge node is used for additional manual masking over and above the segment mask. Now add the SAM2 segmentation. Disable the Keep Model Loaded. This way it will free up VRAM. Add the Florence 2 coordinates and connect it with the data and B boxes. This node processes the data from the run node to extract coordinates. These coordinates represent positions where particular objects or features are located in the image. The coordinates are then passed on as a bounding box to the segment anything model. Now connect the SAM2 model and image. Add an image and mask preview node. Connect the mask and image. Change the value to 0.8. Now, add a pixel-wise mask plus mask node. Connect the SAM2 and the preview bridge mask. Add a switch for the mask selection. Connect mask plus mask first. Then, the preview bridge. And finally, add a load image as a mask and make the connection. Connect this with the Gaussian blur and grow mask nodes. Add a clip text encode and get the clip from the Get node. Convert the text to input, add a CR text node, and set it as InPainting Clip L. We will require this InPainting clip later on in the workflow for upscaling. We only need the positive conditioning. However, the InPaint model conditioning node requires a negative input as well. Add the Flux guidance and pass on the InPaint conditioning via conditioning 0 out. Connect the VAE and pixels. Use the grow mask output for the mask. The Flux model sampling will be at the default values. Use the size and width accordingly. If doing image to image, then in painting, use the resize width, height. Add a differential diffusion node after the model sampling. Add the Flux sampler and make the connections. Only use the positive output from the InPaint model conditioning. For InPainting, the beta scheduler doesn't work that well. Simple or SGM uniform works the best. Connect the noise seed with an RG3 node. Randomize the seed and expand on the mask if you don't get the desired results. Add the remaining nodes. Set this output as InPaint image. We will use it later on for upscaling. At this stage, you can also add another purge VRAM node. Group them and name the group SAM2 and InPainting. Disable the sampler and finalize the mask first. Enter keywords for the selection. Ensure that you end each keyword with a comma. If it cannot mask some things, you need to manually draw the mask in the preview bridge and ensure the final mask output has no gaps. For example, these hairs and whiskers should also be covered in the mask. From my experience, the output is very sensitive to the mask shape and what's included. I have already fine-tuned the mask and will use the load mask option. There are a couple of things you should note. Keep the prompt simple. Don't use any LLM. Ensure that the InPaint model source is the same as the original generation, with or without LoRA. Use the same Flux guidance for consistency. The purpose of InPainting is different. You can use it to fix minor artifacts within the output. If you decide on a composition, you can then use it to change subjects, like in this example, while maintaining 100% consistency overall. Add a switch and connect both the 1x and InPaint image via the Get node. Then, convert the select to input and connect it with the settings in Paint. Selecting 2 here will now push the InPaint output for upscale. Flux is very different. Latent upscale is not recommended since it changes the original generation a lot. We must maintain the original image consistency, especially since we now have text. This is the only method where I can retain text consistency and add details. It is essential to choose 2 different upscalers trained for various image types. Using any other upscale model at this stage will not guarantee the same results. I have tested SwinIR and some other upscalers, and the issue with them is that they oversharpen the images and spoil the soft bokeh in the initial generation with sharp, weird lines. I will link both upscalers. I have downloaded them from a reputable source. The first upscale adds a lot of details and is specifically trained for AI-generated images. This stage will upscale the image 4x. We downsize it by 4x and pass it through the Flux sampler at 0.2 denoise. Set this as the upscale model. The model is a 4x upscaler, so scaled by will be 0.25. The upscale method is Lanczos. For all upscaling processes, we will use VAE tiled encoders and decoders with a tile size of 1024. Now add the Flux sampler. Denoising will be at 0.2. Change the seed to something other than the 1x image. Keep the step sampler and scheduler the same as the original. Set this output as 1x details. Add the purge VRAM and organize into a group called Flux 1x add details. For the next upscale, we should calculate a new width and height. Use the Python Gauss math expression to multiply the a value by a factor of 1.25. Note that this is an approximation since the upscale is about 1.26x. Also, there is no need to consider the image-to-image resize dimensions. At 0.2 denoise, it makes no difference to the model sampling. Copy all the nodes from the 1x add details group and paste as shown. We only need to adjust some values. The switch is not needed. Change the image input. At this stage, change the upscaler to face up. This upscaler is trained explicitly for non-AI faces. So this, by default, adds softness to the upscale. If we use the same upscale model as before, you start seeing sharp lines where they are not needed. Now, this part was a bit tricky because downscaling it by a percentage that equals 1.25x upscale doesn't happen in Comfy. Convert the scaled by to input and add a float constant from Kajai nodes, which has 3 decimals. Don't add these nodes, it's just for explanation as to why 0.315. Suppose you take the original width and multiply it by 1.25x. The output should be 1680. However, in the upscale, we multiply by 4 first. That brings the resolution to 5376. Now, when we multiply this by the value in B, it becomes 1693. This number gets rounded off by Comfy and it's the closest to the original. And multiplying by this factor makes it approximately 1.26x upscale. So 0.31 would give you a rounded off resolution of 1672, whereas 0.315 would give you about 1688. Also note that the 1.26x, 2.52x, and 5.04x upscale factors are calculated from height rather than width. So they are approximate upscale factors. Reduce the max shift to 1. This will further maintain consistency. Set the output to 1.261x upscale. Group and organize the nodes. For the next upscale, we will do a 2x upscale and will no longer use Flux. Use a checkpoint like RealVis-XL. Add clip conditioning as per checkpoint. Make a switch to either use the clip L or the InPaint. Set it up as shown. Add Ultimate SD Upscale with half tile plus intersections in chess mode. For this upscale group, use the upscale model too, as in the previous group. We still don't want to use the sharper upscaler. Set this output as 2.52x upscale. There are two reasons not to use Flux K-sampling. The first one is that it is too slow at this stage. The second one is that Flux beyond 1.5 upscale causes vertical lines. I don't know if it is a bug or the weights. I was getting that consistently during testing, then Comfy updated, and I changed the workflow. So, I never checked with the latest version of Comfy. The last 5x upscale will be without sampling. Same as before, but now use the first upscale model. And downsized by 50%. This process is very heavy on the system RAM. Do this upscale only if you have 64 gigabits or higher. The last group would be the post-processing group. And this is entirely optional. Add Auto-Adjust version 2 node and set the strength to 50. You can use this node to manipulate the colors, temperature, or saturation. Add a levels node and set the black point to 5. That should help with the contrast. And set this output as the final image. Add an RG3 comparer node. Use Git to pull the set image outputs for easy comparison. You may not be able to run every upscale unless on a 4090 and 64 gigabytes of RAM. The workflow is designed to skip the last upscale parts. For easy management, add a fast groups muter node from RG3 and custom sort it as shown. Duplicate and add multiple of these as needed. I will run the entire workflow with max upscale enabled. I learned that if you add disable smart memory in Comfy, all the VRAM issues go away for some reason. Comfy uses smart memory management, but it's buggy. At least, I think it is. When enabled and loaded, the Flux model uses 90 to 99% of the VRAM and slows the generation 1,000 times. The second generation then comes out fine. Third, again, it slowed down. It comes to the point that a 1.5 minute generation takes about 15 minutes. All the VRAM Flux issues disappeared when I added this to the run.bat file. Even with 2 LoRAs, the system used 70 to max 80% of the VRAM. We'll leave the command and instructions in the description. I could keep my video editing software open, record the screen, and do the generations without issues. Also, Comfy recently added ControlNet support for Flux. I will update the workflow after adequately testing. At the time of this recording, it was crashing. GPT-generated unified format, or GUF, basically will allow you to download quantized versions of Flux and use them on lower VRAM. I could not fit GUF in this video. Also unsure if it's complicated enough to warrant another tutorial video on the channel. I haven't played around with it. So let's see. You can see the upscale quality and how it maintains consistency. The Schnell version can be used with the current workflow, but you have to remove model sampling and Flux guidance nodes, change the clip conditioning to single, and reduce the steps to 4. You can use the LLM, but there is no need for the summary. Anyhow, I hope the tutorial was helpful and you learned something new in ComfyUI. Until next time.